Hello and welcome. Today we are going to talk about water characteristics and water quality parameters. So the learning objectives for this week's lecture are to describe the structure of water molecule and the role of hydrogen bonding. We will also look at some of the essential properties of water, and we will also identify key water quality parameters that are used to characterize source water and drinking water. Okay, so some of the terms and concepts that we are going to be looking at. We're going to look at size and shape of water molecules, the space between molecules, polarity of water molecules and hydrogen bonds, some properties of water, then dissolution, dissociation, salts, ions, hydrophobicity, hydrophilicity, and some water quality parameters like turbidity, dissolved oxygen, pH, conductivity, TDS, alkalinity, and hardness. So, let's start with the molecular structure of water and some of the key properties. So here is the bare bones structure, the molecular structure of water, H2O. So the water molecule has two hydrogen atoms and an oxygen atom. So what you see here is this in the middle. So the water molecule is the structure resembles a tetrahedron, and so with equilateral triangles facing the equilateral triangle faces, and on two sides of this tetrahedron are the hydrogen atoms, and in the center is the oxygen atom, and then the uh, orbital clouds of oxygen on the other two ends. There is a partial positive charge on the hydrogen ions because the shared electron bond between hydrogen and oxygen is more towards the oxygen than hydrogen, so that leaves a delta positive charge. Overall, the molecule is neutral, but there is a partial positive charge on the hydrogen and then the partial negative charge on the oxygen, which balance out, and then that makes the water molecule neutral. But what it does, it creates a dipolar structure, or also called a bipolar structure, which facilitates interactions with other molecules or ions, and it results in what we know as hydrogen bonds. So it forms hydrogen bonds, and that leads to unusually high density and cohesiveness for water. So these hydrogen bonds, you can see this. So this image is depicting the formation of hydrogen bonds within the water molecules themselves. And the hydrogen here is hydrogen bonded to the oxygen, and so forth. Technically speaking, one water molecule can form up to 4 hydrogen bonds, but at room temperature, typically on average, there are 3 hydrogen bonds that typically exist. And then water can also form, as we'll see, these bonds with other molecules, which lead to some unique properties, as well as dissolution of salts and so forth. Okay, density of water. So here we see the density. This plot here shows the density of water as a function of temperature. So if you look at it on the bottom of the x-axis here, temperature at 20 degrees Celsius, the density, as the temperature reduces, density starts to increase, which makes sense because as the temperature reduces, the thermal motion, the kinetic motion of the molecules reduces, leading to a more compact structure. As you can see here, it shows the liquid here, and then it becomes more and more compact, and it reaches a maximum point. The maximum density is at 4 degrees Celsius, and from 4 to 0, what happened is something very unique. The molecules now, instead of compacting further, they start to form this hexagonal structure here of ice, and which actually is more organized and more and less dense than the water at 4 degrees Celsius. So when you see right at 0 degrees Celsius, when ice forms, this hexagonal structure takes shape, and uh, the density, rapidly reduces, and then again starts to increase as the temperature reduces further. But this phenomenon it has very profound implications or ramifications in winter. One very obvious is that this is what makes the ice float and not sink. Usually any solids, any rocks, they sink in the water. But ice, being less dense than water, will float on water. As we know, the ice floats in water. So in winter, the denser water at 4 degrees Celsius sinks, while lighter ice floats, which insulates the aquatic life below. So it prevents a complete freezing of water bodies, and it leads to sustaining ecosystems. That has a big contribution towards that. And then in lakes and reservoirs, the maximum density at 4 degrees Celsius plays also a role in seasonal mixing and stratification that happens, and that phenomena that promotes nutrient cycling during spring and fall turnover. So it has some very wide biogeochemical ramifications, as well as ecosystem implications like sustenance of aquatic organisms in wintertime. Now, surface tension of water. We talked about hydrogen bonds. Strong hydrogen bonding creates a cohesive surface layer, and the surface molecules experience an inward force. They try to minimize the surface area, which leads to a strong, you can see this clusters they form on the surface, and it's called a flickering cluster model because it's never static. The bonds form and break and form, and so it's called a flickering cluster model. It's dynamic, and dynamically the bonds keep shifting in water in real time. And then this high surface tension, it leads the water to have this inward pull, and which leads the water to form these spherical drops to minimize surface area because of this inward pull. And so what does the surface tension mean? What are the implications of the high surface tension of water? As you can see in this photo here, of course, water can support small organisms on water surfaces. It also enables capillary action. Water can, in small capillaries, water can rise um, spontaneously because of capillary action, and which helps in water and nutrient transport in plants. Environmentally speaking, as we discussed, it shapes the surface tension. Of high surface tension leads the water droplets to be spherical, which aids the water cycle. It also provides a stable surface for microbial and aquatic life, the water surface. And then there are like a lot of everyday applications because of the surface tension. It impacts the cleaning efficiency and foam stability of water, and also affects the spread and behavior of contaminants in water. So surface tension has also some pretty wide-ranging implications. Let's talk of heat capacity. So heat capacity, denoted by C sub P, is defined as energy required to heat a certain mass of a substance by a certain temperature. And water can, because of some of these hydrogen bonds, water can absorb a lot of heat and store heat without changing its temperature significantly. So water has this capacity to hold a lot of this heat, and therefore it helps in regulating temperature of our bodies, regulating the temperature of the earth, and so it leads to climate moderation. That's why we see coastal regions, coastal cities, they have more moderate temperatures. They don't see wild temperature swings because the water nearby that acts as a big thermal sink, and this high heat capacity also leads and to ecosystem stability because it provides a consistent thermal environment for aquatic life. There are not, as we said, a lot of wild swings in temperature, and it reduces temperature fluctuations. And then for the same reason, the water is used as a coolant in industrial processes and also for renewable energy storage. On the flip side, this high thermal energy stored in water, it fuels hurricanes and it delays seasonal temperature extremes, which sometimes impacts agriculture and urban planning. The heat capacity of water also helps regulate biological mechanisms, stable body temperatures, and metabolic processes in living organisms. Okay, moving on to solubility in water. How do we characterize the water or solute interactions? Solute, I should define, solute is anything we are trying to dissolve in water. That's called a solute. And the water is the solution. Solution is the substance in which you're trying to dissolve the solute. So, and dissolution is the process of dissolving the solute in the solution. So dissolution, technically, it's surrounding of individual molecules of solute by water molecules. So here again, hydrogen bonding comes into play. So if something has to dissolve in water, basically that molecule has to form hydrogen bonds with water molecules. So hydrogen bonds between water molecules have to break, and then the solute bonds have to break, that to promote dissolution, and then you have to form bonds between water and the solute. So anyway, so basically you have to break existing bonds and then make room for these new bonds between the water and the solute. And all of this process is governed by two factors: the bonding energy and the thermal kinetic energy of the molecules. So it's a statistical process, and the balance between whether the bonding energy is more favorable than the kinetic energy or vice versa will lead to a molecule being hydrophobic or hydrophilic, meaning hydrophobic meaning it's, or hydrophilic is water loving. It dissolves in water well. Hydrophobic is water fearing, meaning it doesn't dissolve well in water. So you can define substances hydrophilic or hydrophobic depending on their dissolution capacity in water or solubility. Now some compounds dissociate completely, or that is split apart when they dissolve. And the compounds that dissociate extensively and they release ions in the process, they're called salts. NaCl, sodium chloride, is a good example of such salts. And the positive ions, like the sodium ion, is the cation, and the negative ions, like the chloride, is the anion. And all ions are hydrophilic, water loving, because they can form hydrogen bonds readily with water molecules. So here is an example. So this is salt crystals, and these are ions in solution. So here you can see this sodium ion, for example, it's forming these hydrogen bonds with different water molecules, and so it easily gets dissolved in water because of its strong ionic charge. And then here's an plot of relative abundances of different ions in terrestrial waters. So you can see some of the ones on the right, which are highly soluble in natural waters, like sodium, calcium, magnesium, nitrates, and chlorides, and so forth, and sulfates. These usually have high solubility in water, and for the reasons we just discussed. And so it's makes sense that they have relatively high abundance. And some of them also have natural sources, geological rocks and others. But then because of their ionic charge and the capacity and thermodynamic favorability to form hydrogen bonds with water molecules, that leads to more or higher relative abundance in natural waters. Bicarbonate is a bit of an anomaly in the sense that even though its uh, solubility or hydrophilicity is not as high as some of the other ions, it still has a relatively high abundance in terrestrial waters because there's a very um, profuse supply of bicarbonate into or carbonic acid or bicarbonate into water through the atmosphere. The carbon dioxide in the atmosphere gets dissolved in water to form carbonic acid, which dissociates to form bicarbonate ion. We'll discuss more about this the carbonate bicarbonate cycle, but yeah, we can see how the solubility impacts the constituents in terrestrial waters. Okay, now let's pivot to a related but a different topic: water quality. Why do we care about water quality? Well, it's for very obvious reasons. We want to make sure we have safe water for drinking, for recreational opportunities, and in our healthy coastlines, and for just environmental, human, plant, animal well-being. We want water is the very basic and critical supply, critical ingredient for human, plant, animal life. We want that to be uh, of and preserve that purity of water. Okay, so what different parameters do we measure for source waters and drinking water? The different parameters that we measure: physical, it can be measured temperature, taste, odor, color, turbidity, pH, dissolved oxygen, alkalinity, hardness, inorganic or organic substances, different chemicals like disinfection byproducts. Microbiologically, we measure pathogens, coliforms, and in wastewater, we measure some of these similar ones like pH and temperature, but then also we measure COD, chemical oxygen demand, biochemical oxygen demand. Some of you might be aware of these terms and these uh, metrics. We'll talk more about these as we go through the course. Then we measure this different solids in wastewater: suspended solids, fixed solids, volatile solids, and then of course we measure the nutrients, nitrogen and phosphorus. So this is not an exhaustive list of water quality parameters, but gives you an idea of the kinds of things we measure to quantify water quality. And then here's a quick example of water and wastewater quality. In the left, you can see this is Mississippi River in Louisiana, and there's hardness, total hardness, calcium hardness, magnesium hardness in milligrams per liter CaCO3. There is iron, there is alkalinity, and so we'll discuss this turbidity. We'll discuss a lot of these different metrics and how to measure them, how to calculate them. For wastewater, typically we report the TDS, the total dissolved solids, total suspended solids, the COD, BOD, the nitrogen, phosphorus, and also alkalinity and pH. Okay, turbidity. What is turbidity? It's we understand uh, what turbid means. It means cloudy. If the water is turbid, it's cloudy, and it's due to the insoluble particles of soil, organics, microorganisms, and other materials that impede the passage of light through water. It's measured in NTU, which stands for nephelometric turbidity units, and you can see here uh, this schematic. It shows that how as you go from right to left, the NTU's value increase and the cloudiness of the water also increases. And we use a turbidity meter in the lab to measure the turbidity. And okay, a quick question is, what's the relationship between turbidity and color? I encourage you to pause the video and think about that answer to that question. Well, turbidity can cause color in water, but color itself is not turbidity. You can have colored water but completely clear without any cloudiness. So it's sometimes it's easy to conflate the two, but wanted to point that out, that turbidity and color are uh, two distinct things. They're not. They could be, but they don't have to be related. Dissolved oxygen, DO, referred to as DO in short. It's another important parameter that's measured for a lot of terrestrial waters, because you need more than 5 milligram per liter for most aquatic life. And usually DO, from atmosphere, the DO is equilibrated into the rivers and water. So it's usually in rivers and lakes and streams. It's usually close to saturation. How do you figure out if your water or in a lake or any sample, what's the saturation of that? Because the solubility of oxygen and water is highly temperature dependent. So there's this chart that you could use. So here on this straight line on the bottom, it shows the oxygen in ppm. So you could take a meter and measure your oxygen content in a given sample, and then you could also measure the temperature, and then you say you have the temperature here, and then you have the oxygen solubility. So then you join the two, the top and the bottom. It'll give you what the saturation level is. Is it 100%? Is it 90%? Is it 80%? And so forth. Usually for lakes and streams, you have more than 90 or 95% saturation. pH, again, we have all heard of pH, and it indicates the hydrogen ion concentration in water, which is related to the acidity. And this we're all familiar with this chart or the scale, the pH scale. Around 6 to 8 is neutral, and then as you go below 7, the water becomes more and more acidic, and as you go above 7, it becomes more and more basic or alkaline. So raw water and tap water usually ranges from 6.5 to 8. Note how mathematically we calculate pH. It's a negative log to the base 10. Important that to the base 10, not to the base e, of negative log to the base 10 of hydrogen ion concentration measured in moles per liter. And the pH in natural waters is controlled by the carbon dioxide, bicarbonate, and carbonate equilibrium. As I said, we'll talk more about that when we talk about alkalinity. And temperature also affects equilibria and the pH. So, well, what's the CO2, CO3, and H2CO3 equilibrium? Why is the carbonate buffer system important to living organisms? And how is this equilibrium affected by temperature? So we will answer some of these questions in one of the future lectures. Okay, some other things that we usually measure, some other parameters that we measure for water: conductivity, TDS, which stands for total dissolved solids, and ionic strength. And so they're related. We'll talk about how they are and they're not related. Conductivity measures the water's ability to conduct electricity, and which is determined by the dissolved ions in water. Typically, higher ion concentration means higher conductivity. Now, total dissolved solids. This represents the total concentration of dissolved substances in water: salts, minerals, metals, but something to note it's different from conductivity, because for conductivity you only need ions, not neutral species, but total dissolved solids would also include any neutral species that is dissolved, not necessarily ions, while conductivity uh, would would include only the ions, charged ions in the water. So there is some sort of a relationship and between conductivity and TDS, although it's not completely proportional because of the reasons I just mentioned, but there's some kind of a rough relationship that's defined in the literature. Ionic strength. So ionic strength, it quantifies the total ionic concentration in water. You can calculate this mathematically with the formula given here on the screen, which includes concentration and charge on the ions. So this will not include neutral species. We will do a little bit more deeper dive into ionic strength in one of the future lectures. But the difference between conductivity and ionic strength is, it just quantifies, you can calculate it mathematically knowing the concentrations of different ions, but it's slightly different from conductivity because conductivity depends on both the ionic strength and ionic mobility. If there is a high ionic concentration, that would lead to high ionic strength, but that can reduce the mobility per ion and in turn also reduce the conductivity. So you see there's a slight difference between conductivity and ionic strength. But the three of them, the conductivity, TDS, and ionic strength, they are somewhat related, but not exactly. And then I wanted to just comment on this photo right here on the right. This is in August 2023. Some of my collaborators and students, we were at the Matanuska Glacier near Anchorage, and we were looking at the water quality of the glacier water. And here we can see we are measuring with field meters, we are measuring the TDS, DO, conductivity, pH, temperature, and a lot of other things that's we're not discussed here in this lecture today. Alkalinity and hardness. Alkalinity, it's a measure of the water's ability to neutralize acids. Also could call it a buffering capacity of water. So if you have high alkalinity, you have high buffering capacity. And it's the bicarbonates and carbonates and hydroxides. These are the main contributors to alkalinity. And it's important for maintaining stable pH in aquatic systems and preventing rapid acidification. Hardness. Hardness is caused by the divalent cations, which is the positively charged ions, primarily calcium and magnesium. So note, while alkalinity is contributed by the anions, that's bicarbonates, carbonates, and hydroxides, hardness is contributed by cations, the positively charged ions. And as we know, hard water impacts scaling in pipes, soap efficiency, the taste of water. You can classify hardness as total hardness, sum of all hardness causing ions. Then there is carbonate hardness, the ions which are associated with bicarbonates and carbonates. And then there is non-carbonate hardness, which is the hardness caused by other salts like chlorides or sulfates. Again, we'll talk about alkalinity and hardness in a separate lecture, and we will also look at how to mathematically calculate some of these things. So with that, thank you for paying attention, and we'll meet in the next lecture. Thank you.